Okay, I've had to turn off a bunch of lighting. I hope this is still bright enough. It looks good in the viewfinder. I am presently looking on the anode of the oscillator. And you saw how distorted the sine wave was. I was looking for ripple, but there's only about, let's see, that's 5 times 10, that'd be 50, but that's per division, so we're looking at about 20 millivolts of ripple. Not great, but not horrible. It shouldn't be causing that nasty distortion we're seeing. However, if we look here in the schematic, it says 190 volts. And can you, no, I don't guess you can see the voltmeter. Let me, there we go. If I put, this is almost out of the shot now. If I put the voltmeter on that same point, there's only 110 volts DC there, which is making me very suspicious. Wish I could get everything in the shot. Maybe if I back the camera up, but then it's you're gonna lose detail. This 0.5 microfarad at 400 volt, this is the one I think that was leaking all its bodily fluids all over the bottom. I suspect this may be highly leaky, so what I'm going to do is disconnect that guy, probably easier from this end, and we'll take a look and see how bad that capacitor is. That may be what's dragging my voltage down. So let me get that disconnected and we'll be back. No, actually I'm going to do something else first. If we look at the circuit here, take a look at the schematic. Yeah, I think you can see that all right. This is our anode of the oscillator. Actually, it's a Wien bridge oscillator, so these two tubes are basically an amplifier with feedback. But this second amplifier, which is part of the Wien bridge oscillator, this 6K6 is supposed to be biased at 0 volts. Now this is supposed to be 190, and I'm presently seeing 110. Therefore, I suspect this capacitor is highly leaky. If I am right, I think that says pin 5. Yeah, that's pin 5. This is supposed to be 0 volts on this grid across this 470 k ohm resistor to ground. If I've got voltage there, then I know for sure this is leaky, and that's probably most of my problem. So that was pin 5, pin 5. And if we come down here a little bit, there we go. Oops, a little top heavy with the transformer up above. So here's our oscillator. This is our 6SJ7. Here's our 0.5 microfarad coupling capacitor. And that goes down to pin, I turned off all the backlighting, pin 5, which is there. 1, 2, 3, 4, 5. Yeah, that's where that wire comes up, because there's my, I want to say it was 47K. Yeah, there's my 47K resistor right here, yellow, violet, yellow. So there should be 0 volts. Oh, I'm on the 150 volt scale and showing voltage. 50 volt scale. 15 volts. There's over 15 volts right there. I bet that resistor's a little warm. Yeah, just barely. So there's my drop on my anode. That's probably why the oscillator's shutting down, and that would certainly contribute to all the distortion we're seeing in the sine wave. So this 0.5 microfarad has got to go. Absolutely leaking. This should be 0 volts, and I've got 15 volts there. Okay, I'm going to take that out. I'm going to replace it. I'm not going to bore you with watching that. I'll just take care of it and be back. Okay, this leaky old paper cap is out. There's no manufacturer's name on this thing. It does say made in USA, 0.5 microfarad at 400 volts, but no name. Junk box. over here in the unit, we have a brand new Sprague. It doesn't say Sprague on it anywhere, but it came from the Sprague lady. I know where it came from. Half a microfarad, and this one's rated at 1,000 volts. So that one should have no problem handling the 190. And if we take a look, oh, I should swing this up here. Let me turn off the backlights. There we go. We now have a nice sine wave, and it doesn't shut down anymore. All the bands work. There's actually a sine wave there. It's just too low in frequency. There we go. Is that showing up? Yeah. That's all the way up to supposedly 200 kilohertz. And still a pretty good looking sine wave up there. So, that solved that problem. I'm sure we still have some more leaky caps in here. We will take things one step at a time, but that's pretty decent looking. And our grid, what do we have on our grid? It's back down here, the voltmeter. Our grid, which was sitting at 15 volts previously. I'm going to stick it right on there. That's the 1.5 volt scale, and it's still sitting on 0. So, that solved that problem. That's where all the distortion was coming from, is that grid was being biased with 15 volts, and it's supposed to be 0. Okay, through the magic of YouTube, it is the next day. I was tired and shut down for the night. When you start getting tired and you're working on this equipment, it's time to stop, because you can die. We've got 275 volts on each side of the secondary. That's 550 volts AC. That'll give you a dirt nap and a heartbeat if you get across it. 300 volts DC after it's been rectified. That'll also give you a dirt nap, never mind the 115 volts coming in from the line. These sets can kill you. You get tired, you're not sure what you're doing, shut down before you get hurt. Enough said. Okay, next day we're working on this. The cabinet is outside. It's had its second coat of paint. Yesterday we sanded and primed it. So the cabinet will be in good condition when we're finished here and when the paint dries. In fact, I'll probably toss it in the oven this evening for a couple hours at 200 degrees just to finish burning off the volatiles. But we'll wait for the sun to dry it well for at least 6, 7, 8 hours out in the sun. Okay, where are we? We're here. So far it seemed to be looking good. Let me zoom in a little bit here. Yep, that's still in focus. Okay, good looking sine wave, you say? Yeah, not bad. Looks pretty decent. Not so much. We've got issues. I am going to reduce the gain, the output of the unit, and I'm going to increase the sensitivity of the scope here and reduce the gain some more, and we'll increase the sensitivity of the scope. What are we starting to see? Look at the spikes. Now at first sight you might say, oh, that's your LED lighting. No, that's actually coming from within the unit. That is coming. Yeah, I'm going to have to zoom out here to do this. There we go. That is coming from the square wave generator. Now looking at this, the square wave generator appears to be utterly bypassed. So how the heck is it, when the switch is in this position? If I went to the square wave setting, you can see there's a square wave forming. Let me increase. Whoop. You can see we have a square wave. Sine wave, but look at the noise on the sine wave. There's your square wave, there's the noise in the sine wave. When this is in the sine wave position, one would think that circuit's utterly bypassed. There's no connection to anything There is still current going in through this tube. It's impressing that evidently on the ground. However, I think it's the wiring associated with the slide switch that changes between sine wave and square wave. The wires are probably too close to one another and capacitively coupling. How do I know for a fact that that's what the case is, you're saying? Well, I am going to pull the 6SN7, which is the square wave generator. And there you have it. That has completely removed any noise from the signal. Looks like it's blooming a little bit. The camera sure does like green. That any better? Yeah, a little bit, I guess. This is the 6SN7, which is the square wave generator. If I put it back in the circuit, as soon as the filament warms up, you'll see the spikes come back. There they are, growing right up out of the sine wave. So we'll have to address that, because that will certainly add to our distortion, our sine wave distortion. We'll have to eliminate that. Another problem we have is this. I'm going to turn this down to minimum. Right now we are on AC coupling, and I am going to set this to there. We have the, in fact, I'm going to increase the sensitivity of the scope here to its maximum. And we'll go back to AC. Okay, we have, you can see the huge spikes. Let me turn the intensity up ever so slightly. We are now on 5 millivolts per division, so we have 5, 10, 15, almost 30 millivolts of spikes, and that's with the sine wave turned all the way down. If I start to turn it up, you can see they're very clearly in there. All right, why am I doing this? There's ground. I'm going to flip this to DC coupling, and the trace is going right off. If I go back, 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 right now we're on 50 millivolts per division. There's ground. Let me reset it. The scope DC balance is off a little bit. Not surprising for this old beast. There's ground. There's 50, 100, 150 millivolts of DC on the output. What does that tell us? Well, if we look at the schematic here, I'll zoom back out. Oops. There we go. We come down here to our schematic. Here's the output, 6K6. Here's our output jacks. There's a 10K resistor shunting the output, and from this cathode follower we have a 20 microfarad capacitor to the output. But I'm seeing DC on the output, which means this 20 microfarad cap is leaking, and it's not only leaking a little bit, it's across a 10K cap. It has a 10K load on the output, pulling it down, and it's still 150 millivolts of leakage. If you took this resistor out of here, this would float right up to the 67 volts that's on the cathode. Now, I'm going to put a 1,000 ohm resistor. How's that for an antique resistor? Isn't that a beauty? You can actually see on the end where there's an outer cylinder that has been backfilled once the resistive element was put in there. God knows how old this thing is. I did measure this. It's 1100 ohms. It's supposed to be 1,000. Actually, it's 1108 ohms, which means it's 8 ohms outside of its 10% tolerance. But it's close enough for our purposes. I am going to put this across the binding posts on the output and see what effect it has. We'll put the camera back up on the scope. I'm expecting it to pull it down quite a bit, and it has. This is supposed to be terminated into 1,000 ohms, so I'm giving it 1,000 ohms of termination right now. But we still have DC. There's ground, so we're still looking at, let's see, that's 20 millivolts per division. That is still almost 20 millivolts. 10 millivolts, that's 15 millivolts if our ground is still there. Our ground reference point is still there. Again, this is a 30-something year old scope that's never been calibrated, so there we go. We still have 15 millivolts because we're in the 10 millivolts per division and we're 1.5 divisions up. So that coupling cap, that 20 microfarad coupling cap has got to go. Actually, every capacitor in here has to go. Let's be upfront about that. What I'm doing is just an educational exercise, if you will, showing you the symptoms of what you'll find with bad capacitors, bad resistors, whatever we run across as we keep going into this. I was not going to dig this deeply into this unit, but I overnight decided, what the heck, I'll make this a two-parter. At some point I'll split this video, and if nothing else, hopefully somebody out there will find the troubleshooting useful. I hope. I know this is nothing earth-shattering, but it is showing you what happens when these capacitors leak. It is showing you how to go through here with a voltmeter. This can be found with a voltmeter, by the way. Just for the heck of it, I'm going to take the load off of the output again, and we will come down here to the voltmeter. Let me hook the voltmeter up. We're on DC volts. Now, bear in mind, this is an output, audio output. There should be no DC here whatsoever. This should be absolutely DC free. And there you go. Almost 200 millivolts. We're on the 1.5 volt scale, and we're looking at 1.8. So, and if my 0 is set correctly. Fun with vacuum tube voltmeters, as they warm up, they drift a little bit. So about 1.5, 150 millivolts, which is what the scope was showing. So the voltmeter agrees with the scope. We have a leaky capacitor on the output. So let me go ahead and change that one cap out. We'll fix that one problem. Let me flip this thing up. It's this output cap right here. So I'll change out that electrolytic. We will put a brand new, what do we got here? We must have something 20 microfarad. Sure, we got 22 microfarad, close enough. We certainly don't need a 450 volt cap, though. That's a waste of a good $5.40 for that one capacitor. Let me go see if I can find a lower voltage 20 microfarad. We certainly don't need to be wasting a $5 cap on the output. And there's only 67 volts here. If I got something 20 microfarad in the 100 volt range, I'm going to use that instead. Okay, let me go look for a cap. Alright, instead of using a $5.50 electrolytic, axial lead electrolytic, I had a bin full of these no-name 22 microfarad at 400 volts. And since this only operates at 60 volts, it'll be perfectly fine in there. These were probably $1 a piece. I forget what I paid for them, but I've got a bin full of them down there that I use for non-critical applications. And I tested this using the solar capacitor examiner, this guy right here. Ran the voltage up to 375 volts, which is about 25 volts below its rated working value, and the leakage dropped down to an immeasurable level. It was somewhere down below where the meter on the examiner was capable of reading. So it'll be fine at 60 something volts. It's only passing audio. Why was it important to change this in the first place? Well, you don't want any DC bias on your audio. especially if you're working with an amplifier that's DC coupled on the front end, because this will throw off the biasing of the amplifier. So if you're doing any testing, you want to make sure that there's no DC bias on your audio. Now there are applications, I can't think of anything off the top of my head, some units will allow you to introduce a DC bias, but in 99.9% of the cases you won't want any DC writing on your audio, so that will block it, that will take care of it. We'll move back underneath here and start going through the rest of these capacitors. I've got replacements for them. It's amazing. That gets replaced with something like this, as does the one that's down underneath here. That will also get the same treatment. That'll get replaced with that. And the last waxy that's over here will get replaced with this. Then we'll have replaced all of the paper capacitors. We'll still have these three electrolytics, the double section can unit here and the double section can unit here are still there. Now remember, we only had a handful of millivolts of ripple on the AC. So at this point in time, I'm not too concerned about the can, or especially this can electrolytic. I haven't done anything to look at this one yet. This is probably bypassing, I'm guessing. What have we got here? 50 micro, yeah, that's the bypass for this lamp for the cathode bias. So we'll want to take a look at that, because that can affect linearity and distortion. One thing at a time. We're going to go through here and take a look at the effect that one might have, and this one might have, and this one might have. So let me get set up for that. Alright, phone rang and I had to go off and do a couple errands. I forget where exactly we were at, but I'm just going to pick up and carry on here. This is our square wave generator, and I don't know if you remember. In fact, before I even do anything, let's take a look at what the pattern looks like and see if we can make improvements here. Am I hooked up here? No, I'm not. I don't even have a connection on there anymore. Too many interruptions. Too many interruptions. Let's see. There's ground. Oh, I got a resistor in the front now. We can hook directly on here. How's that? There's that. There's that. All right. And we'll turn up. Whoa. Oh, actually, with a load on there, that actually looks pretty good. Oh, you can't see that, can you? There we go. Okay, sorry about that. I had the power adapter plugged into the camera, but I didn't have the other end plugged into the wall, and the batteries went dead. I know, how unprofessional. Alrighty, let's see here. Yeah, that's actually not a bad looking square wave at this point. I'm really amazed. I wonder if that's just because I put a load resistor on there. Oh no, I got rid of the DC bias as well. I got rid of the DC bias. Let's get rid of the load resistor. That's what it was. We got rid of the DC bias. That cleaned up the square wave considerably. So I don't know if we're going to make any visible improvements now by changing capacitors at this point. Wow, that looks pretty decent. Let's take it up to the max frequency here. Okay, we're starting to round off a little bit. That's band C, that's 2 kilohertz. What's this rated for square wave? I'll bet it falls off pretty good at the higher frequencies. Sine wave, square wave range. Yeah, it says square wave 60 to 30 kilohertz. 60 hertz to 30 kilohertz. Where the sine wave is 20 hertz to 200,000 hertz. So they know it's going to fall pretty badly on its face by the time you get to 30 kilohertz. But let's see how bad it does get here. We'll go up to the next range. And of course that's 200, that's 200,000. It's starting to look a little bit better. That's 40 kilohertz. There's 30 kilohertz, and even that is suffering. It's got some pretty round edges in the beginnings. And that's to be expected. This is, you know, not a modern piece of gear. But down here at the lower frequencies, that's, let's see, that's 200 hertz, and that's 2000 hertz. Is that right? BC, yeah, band C. Excuse me, 20 kilohertz. That's 20 kilohertz, not 2000 hertz. I'm on drugs. This is 2000 hertz, which isn't bad. Not bad at all. I don't know if we're going to make any improvements at all, but let's go back up to the higher frequency where we've got visible rounding. I really don't know what to expect from this. So we've got a pretty rounded leading edge here. The trailing edge looks pretty good. I don't know if we can make any improvement on that, but I'm going to change some of the capacitors and see if it does make any improvement. Is that clear? There we go. You can see the leading edge is pretty rounded off. So, oh, that's what an amplifier would look like that had poor frequency response on the high frequency end. You inject a square wave into an amplifier and take a look at the output on your scope, and if it's rounded here on the leading edge, that means your amplifier is rolling off the high frequencies. If it has rounding on the trailing edge, that means your low frequencies are falling off or attenuated. And if you had a dip in the middle, it would mean the mid-range was falling off. You have, you know, it could be from a tone control or whatever, or just bad amplifier design. So let's change some caps and see if it makes any improvements. I'm going to zoom back out here, and we'll swing this around so we can see the voltmeter again. Is that in the frame? Yes, it is. Good. We have this 8 microfarad and this 003 microfarad cap that are still originals. The 8 microfarad is right here on the output of the square wave generator. That's what's feeding our next stage. We've already changed this, and we haven't changed this coupling cap yet. We changed this coupling cap. So we've got to go through this coupling cap. We've changed this output cap. Let's see how bad this 8 microfarad is. We've got 210 volts on the anode, and if I put this back on sine wave, onto the sine wave position, and leave that cap open, theoretically this should have 0 volts on it. After our initial kick on the voltmeter, it should go to 0 volts, but I've got a sneaking suspicion it won't. Okay, we're on DC, we're on 500 volts. Here's on the anode of the plate itself, 150 volts. And the schematic says 130, so that's close enough. We'll go to the other end. Oh, I'm on the wrong tube. I'm an idiot. Excuse me. Here's the anode. No, what am I doing? What am I doing wrong? 200. I'm looking at the wrong tube. I'm a dope. 210 volts is what we want. Pin 5 of the 6SN7. This is the 6SN7 up here. So 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah, this is the anode. Says calls for 210, and that's 212, 214 maybe, so that's almost dead on the money. This is the capacitor we're looking at. Here's the other end of it. This should be 0 volts. And we're looking at 150 volts on this end of this capacitor. So when we switch that into the circuit, what we're actually doing is injecting 150 volts across this potentiometer right here. And if this capacitor is leaking, which I suspect it probably is, it will affect this 55 volt bias when we switch that into the circuit. In fact, let's see what happens. That's on pin 8 of the 6K6. The 6K6 pin 8 is here. And let's see what happens when I flip in the square wave. See the voltage go up, goes down, goes up. Yeah, maybe it's not staying up. So the coupling cap evidently isn't all that bad, this one here, this 0.25 microfarad, which is this guy here. Oh, 8. What am I looking? Did I cut off the tube? I'm being stupid again. I'm thinking pin 8 here. That's pin 5. 8 is the cathode. If you take a look, I don't know how well you can see that. That sure looked like an 8. That's pin 5. I hate these photocopy schematics. So 1, 2, 3, 4, 5. Even that's not horrible. It looks like this coupling cap isn't all that bad. However, this one is. 1, 2. Let's see what this one does. No, that one's alright too. Alright, I'm going to change this 8 microfarad. That appears to be falling off. 210. Oh, no, it's not in square wave. It's still showing 100 volts on the end of that capacitor, so I'm going to change out that 8 microfarad and get rid of it. I'll be back.